Volcanic eruptions take on many different forms, from seemingly benign degassing events to eruptions that can blow out mountainsides and engulf hundreds of miles of land in ash and lava. The Volcanic Explosivity Index is a relative scale that allows for the comparison of the explosiveness of different volcanic eruptions throughout geological time. The VEI was proposed by Chris Newhall and Stefan Self in 1982 in order to propose a semi-quantitative comparison between poor data and the need in various disciplines to evaluate the record of past volcanism. Before the VEI classification, previous quantification of eruptions were based mainly upon estimating thermal and kinetic energy in the eruption. This was based on estimating lava and pyroclastic volumes as well as column height. In 1980, Walker designed a scheme that was based on 5 key factors: magnitude, intensity, dispersive power, violence, and destructive potential. Most ended up adopting a variation of this method created by Tusa in 1995. Newhall and Self's VEI takes into account similar processes and principles as previous works, including the volume of pyroclastic material such as volcanic ash, tephra, pyroclastic flows, and other types of ejecta, the height of the eruption column, the duration of the eruption, and eruption classifications. Eruptions were assigned a VEI on a scale of 0 to 8. The pair categorized over 8,000 eruptions. This figure, taken from their original paper, shows the number of VEI 3, 4, and greater than or equal to 5 eruptions since 1500. This diagram visualizes the VEI scale and the volume of erupted material that each one represents. Starting at 0, this represents an eruption that produces less than 0.001 cubic kilometers of ejecta. These are therefore the smallest of eruptions and are usually effusive. The next step up, VEI 1, produces between 0.001 and 0.001 kilometers cubed of ejecta. The scale for VEI becomes logarithmic. VEI 2 eruptions are associated with a dense cloud of ash, gases, and volcanic bombs, and are usually classified as strombolian. The plume height is typically between 1 to 5 kilometers, and in the last 10,000 years there have been 3,477 eruptions. An example of a VEI 2 eruption was the phreatic eruptions in 2012, 13, and 16 of Volcanic volcano on White Island, New Zealand, having an estimated eruption volume of between 0.001 and 0.1 kilometers cubed, and a plume height of 2 to 3 kilometers. The island is famously known for the 2019 eruption, which occurred unexpectedly and claimed the lives of 22 tourists and guides. The island has seen volcanic activity for the last 150,000 years. In 1985, the Ruse volcano, Colombia, erupted an estimated 3.5 times 10 to the 10 kilos of tephra, with a total volume of 0.039 kilometers cubed and a plume height of 6.1 kilometers, which firmly put this eruption at a VEI of 3. The eruption generated massive mudflows called lahars, which killed 23,000 people. VEI 3 eruptions are associated with severe avalanche of ash and debris and generally occur on a yearly basis. These are often classified anywhere between strombolian and subplinian. Volcano that many of us will remember is the 2010 eruption of the Icelandic volcano Eyjafjallajökull. The eruption is most famously remembered as the enormous disruption it caused on aviation across Europe and the rest of the world. The second phase of the eruption is deemed to be VEI 4 due to the 0.11 kilometers cubed of tephra erupted and the column height of 8 kilometers, and is classified as subplinian. There have been 421 VEI 4 eruptions in the last 10,000 years, which is a rate of less than 1 per 20 years. At this scale, you can expect the vast columns of ash to reach the stratosphere and be defined as a cataclysmic eruption. Another well-known eruption is the 1980 eruption of Mount St. Helens in Washington. Although an extremely powerful eruption, blowing laterally, taking out the entire side of the mountain, the eruption did not generate that much magma respectively. The total eruption volume equates to just 2.8 kilometers cubed, and so at the lower end of the VEI 5 eruptions. However, it had a column height of 22 to 23 kilometers, seen by this spectacular image. There have been 166 eruptions of a VEI 5 in the last 10,000 years, and these are classified as Plinian eruptions. One of the largest modern eruptions was the 1883 eruption of Krakatoa in Indonesia. The eruption was so devastating it could be heard 3,000 miles away in Mauritius, and pressure waves recorded around the world. The eruption spewed out over 21 kilometers cubed of material, up to 80 kilometers into the air, and resulted in the deaths of over 36,000 people. Over the last 10,000 years, there have been just 51 eruptions of this scale, and are classified as Plinian to ultra-Plinian, with an occurrence of well over every 100 years. The eruption of Tambora in 1815 is known for causing the year without a summer. The eruption is the largest to have occurred in human history, with an estimated eruption volume of 160 to 210 kilometers cubed of material, approximately 30 times the volume of Loch Ness, Britain's largest loch. These eruptions are defined as supercolossal and occur on timescales greater than 1,000 years. In the last 10,000 years, there have been 5 of these ultra-Plinian eruptions, and a further 2 that are suspected to be of this magnitude. The risk of a volcano can be largely considered depending on their frequency of eruption. Yellowstone is an active complex with the potential to wipe out the majority of the US. Yet having only erupted 3 times in the last 2.2 million years, it poses less of a risk than Mount Etna, for example, which erupts nearly 200 times a year, producing streams of fresh lava and the potential for ballistics to hurt people. However, its VEI is far, far lower. Examples of mitigation to risk may be the relocation of homes or buildings, such as in Montserrat, where even the airport had to be moved and a permanent exclusion zone enforced due to recent eruptions. Lahars, which are one of the main killers during large eruptions on glacial volcanoes, can be detected using a network of tripwires and flow sensors, as shown in this diagram here, which allow people more time to evacuate and therefore has the ability to save lives.